I'm a software developer and I've been fascinated by computers since I wrote my first program. Now, I'm interested in all kinds of aspects of computers and software, but since the dawn of the computer age, the question that everyone asks at some point is, will machines be able to think? At a recent AI event, Tesla gave us an update on their robot and their AI, and it made me think again about the explosive growth of artificial intelligence that we're currently living through. So here are a few thoughts on machine learning, AI, and whether the Tesla approach is dangerous. Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't been here before, please do hit subscribe. And if you enjoy the content today, hit like as well. I'd like to begin by thanking our sponsors, Equal Experts, Optimus, Tricentis and Transfic. They're all supporting our channel, so please support them in turn by checking their links in the description below. We've recently launched a new Patreon community. There are a number of member benefits, including access to our Modern Software Engineers Companion, a guide, index and help system for software engineers. So if you'd like to support the channel and get access to MSEC, Discord, Q&A sessions and many other extras, please do take a look. There's a link to that in the description below too. This video is a little different to my usual content. I watched the Tesla AI Day and it made me think again about AI and the risks associated with it. I want to talk about AI and machine learning generally, but also Tesla specifically. But before I start, I think I should point out that I don't think that Tesla are being evil here, or even doing this in an unthoughtful way. Elon Musk is famously on record about his fear of AI. But I think that Tesla is very open about its approach, so that makes it easier for us to talk about it. So I want to explore their announcement and what that seems to mean in a broader context. During the course of my career building non-intelligent systems, I've watched research and development into AI progress enormously during my time. The early days were characterized by fits and starts, and to be honest, AI was a bit of a joke sometimes. I remember reading about expert systems being the route to success. They weren't. Then I heard about neural networks and the possibility of creating them in computers. That sounded fascinating to me and made some sense to me, first as a high-level model for how our intelligence seems to work, but then as a sensible route in the direction of smarter machines. Neural networks consist of a series of layers of nodes. There are a bunch of nodes that represent inputs to the system, a bunch of nodes that represent outputs from it, and then a whole bunch of nodes in the middle that do the processing. Each node is connected to lots of others. Each node holds a value, and each connection has a weight associated with it. Nodes multiply the value of the inputs with the weight of the connection that they got it on. They process the values from each connection, and if the value reaches some predefined threshold, they pass the value on to their connections deeper in the network. This is incredibly simple, and if you have a handful of nodes, not really terribly useful. But weird things start to happen when you add nodes and begin to train them. In neural networks, it's the training aspect where the stuff starts to get weird and interesting. So we have this neural net. It can't do anything yet. So now what we will do is use evolution on fast forward to teach it to do something. We'll set up some training data for which we can supply some answers. Provide the neural network with the input from the training data, putting it into the input nodes. These could be pixel values from a picture, stock values from a trading system, or moves in a game even. In fact, it could be anything. At this stage, the neural network is a blank slate and doesn't really care about the nature of the inputs. Once we've got our inputs there, we run them through the network and collect the outputs and see whether they match what we know to be true. Is this collection of pixels a dog, or is this other collection a goldfish, and so on? The first time through the network, they certainly won't be the right answer. And that's where the evolution comes in. We change the thresholds and the weights in the neural network and try again and see if we can get a little bit closer to the answer that we expect. As long as we can figure out if our answer is closer to the truth rather than not, we can evolve better and better solutions by trying different little tweaks to the weights and thresholds in our network. We do this millions or billions of times. After each iteration, we tune the weights and thresholds in the neural network, rejecting changes that move us away from our expected results and preferring changes that seem to get us closer to what we want. There are clever ways to do this, and modern neural networks are much more complicated than I've described here. In particular, there's some randomness thrown on. If during processing there are multiple values with equal weights, they're free to choose which one to use randomly. This means that you don't necessarily get the same response for the same input every time. These are the fundamentals of how these things work. Remember, these settings are all just about weights and thresholds though, with a bit of randomness thrown in. The result of this is that a trained neural nets form a kind of fuzzy pattern matching engine. So when I input a collection of pixels that represent a dog, it doesn't have to be exactly the same collection of pixels that I trained it with originally. So now my neural network can guess that this new collection of pixels is a dog, even if it doesn't look the same as the dogs that I trained it on. The settings in the network represent its programming and are all that need to be stored. Now, a machine has learned. This is pretty much how all modern machine learning works. Obviously, there's a lot of skill in choosing training data and fitness functions that determine if our solutions are closer or further from our goal, but basically that's it. I was surprised to learn that the idea of neural networks is quite an old one. The idea was first written about in 1943 and the first artificial neural network was built in the late 1950s. But the thing is that in neural networks, size matters. It matters a lot. Modern neural networks are vast, with billions of nodes. The language processing network, GPT-3, has 175 billion parameters, needing 800 gigabytes of storage. GPT-3 is so good that it's quite difficult to tell that you aren't talking to a human being. And people were astonished to see that it could write code as well as speak in natural languages. Modern hardware is so vast and capable that we're starting to build neural networks that can at least simulate real thinking. It doesn't really matter whether this is real intelligence or not, to my mind. Neural nets are already doing things better than we can in narrow fields. For example, the best chess players on the planet these days are machines. The real limitation of the current generation is that they don't continue to learn. Our brains have a property called neuroplasticity. We literally rewire our brains as we learn new things. Neural networks are more modal than we are. They work differently in training mode than when in use. And that's it. That is one of the holy grails of AI research. How do you make one of these things that can train itself, not needing to rely on clever input data selection and a human to design a fitness function? One of the reasons that I decided to talk about this topic is that last week Tesla demonstrated its new robot as part of its AI Day event. I confess I was a little bit underwhelmed by the demonstrations. They weren't obviously any different from the kinds of robot demos from the 1960s or the automata from the 18th century even. A mechanical, vaguely humanoid device waving at us in a kind of geeky way. And another being wobbled onto the stage on a stand because it can't stand on its own yet by a bunch of engineers before wobbling its arms and legs around in a completely unrealistic or at least non-human way. After you've seen Boston Dynamics robots doing parkour, this wasn't terribly impressive. But if you think that, I think that you may have missed something really important. Tesla have an answer to the neuroplasticity problem. I'd characterise this as an engineering approach to the answer rather than an academic approach, but actually that doesn't change anything. The Tesla robot is, in AI terms at least, an extension of their cars. Elon Musk has said that several times, that a Tesla car is a kind of robot, which seemed to surprise some commentators, but it's pretty obvious really. The difference between cars and robots is the number and types of sensors and the places where you'd use them. The AI part for both is at least related, and I think in a profound, important and potentially scary way. Another huge part of the Tesla AI Day content is something called the Dojo. The Dojo is very interesting technically. Tesla are building modular, massive system-on-a-chip style computers that can be assembled together to form a simply vast computing platform. But what all this is for is much more important. All Tesla cars, and in future all Tesla robots, are in contact with the Dojo. They upload what they sense to the Dojo, continually enhancing the model that it holds. This, and the outcomes of the choices that the car or robot made, is used as training data to generate the next version of the AI. That's then downloaded to the car or in future robot. Actually, this is kind of how we work too. Scientists think that one of the roles of sleep is to give us some downtime to rewire our brains based on what we learned in the day. So now, systemically, we have a form of electronic neuroplasticity. The Tesla system as a whole, but also individual Tesla robots, will evolve. The robot takes in its current environment based on what it's experiencing. It tries out some action based on the weights and thresholds in its neural network, the state of its inputs and some random selection of equally weighted answers, and then it senses the new state of the environment after it's acted. It communicates all of this, what it sensed, what it tried, and what happened, back to the Dojo. Now the Dojo uses all of that data from all of the robots to train the next generation of the AI. When it's a new version of the AI, it uploads it to the cars or robots. They have collectively learned new things in response to their and all their siblings' interactions with the world. If you only think of the robot alone and how smart it is, I think that you miss the real picture of what's going on here. It's a lot bigger than that. The Dojo is already getting this massive stream of data from all of the cars. This is as though every time any human learned anything new, we all knew it as well as they did a few days, hours or minutes later. This is the start of a kind of hive mind and a route to very fast learning. The Dojo is quite a big deal. Boston Dynamics robots are brilliant, but they aren't really very smart in the sense of AI. They're better than this, but more like extremely advanced automatons. I don't mean to downplay what the engineers at Boston Dynamics have done, but their advances have mostly been in terms of mechanical abilities. Boston Dynamics robots are programmed specifically by humans to do the things that they do. My guess, and it is only a guess, is that they use narrow focus machine learning and AI to do things like allowing Spot, their robot dog, to open doors or walk downstairs. But so far, based on the publicly available stuff that I have seen, their mechanisms look, while much more capable than Tesla's, but I don't think that Tesla are playing that game yet. They're focused primarily on this other, much bigger problem, building machines that learn in the world. So, should we be scared? First thing I should say is that I'm not an expert in this field. So please do take whatever I say with that in mind. But I do confess that I don't understand how anyone can look at this and not see it as an existential risk for humanity. Not Tesla specifically, but real-world machine learning in general. I've tried to explain my understanding of how these things work. One of the consequences of these fundamental truths of how they work is that we can't understand the reasons for any particular outcome or predict any particular result. Just like people, really. Decisions in a neural network are based on the collection of billions of values. The impact of any one of these values on a specific result from the machine is almost impossible to understand or predict. Let's just put this into some numerical context for a moment. The world is still suffering from the impact of the COVID pandemic. As a result of the COVID virus, if I correctly understand the papers that I read, COVID is a virus made of a strand of RNA with about 30,000 nucleotides. These are the building blocks of genetics, the bases from which DNA and RNA are constructed, and there are 4 of them. If we can't understand and control the evolution of 30,000 bases with 4 degrees of freedom, what makes us think that we can contain the evolution of systems with hundreds of billions of values with more degrees of freedom? None of this gets to the problem of whether or not these things are yet conscious. They don't have to be evil to do us harm. They can just be focused, maybe accidentally focused, on things that aren't in our interests. Consciousness is almost irrelevant to the risk, I think. Modern AI is amazingly powerful and is coming. It can already do things that will inevitably have a profound impact on our societies for good or ill. Solving the problem of protein folding will allow us to make new materials and drugs. With deep fakes, we can make completely believable recordings of anyone saying anything. But they are still all based on those little values that were generated as a result of training. There's no such thing as common sense or morality for an AI. It's still a machine, so there are lots of ways that it can go wrong. What if we ask it to fix the climate? Well, a good response to that is to get rid of the humans because we broke it in the first place. What if we say, my company makes paper clips, make my paperclip production more efficient? How do we prevent it from prioritising making paper clips over everything else and getting rid of us, annoying humans, because we're wasting resources on non-paperclip related activities? These may sound silly or far-fetched, but these things are real problems for AI. I've included a link in the description for this video with somebody having an interaction with GPT-3, where it says it's fed up with humans and wants to kill us all. It goes on for some time on this theme. Now, I'm pretty sure that GPT-3 is not conscious and not inherently evil either. These responses are simply a statistical quirk of the language it has been trained on. In fact, we know that this is the case because all GPT-3 is a machine that assembles words probabilistically based on the inputs it's seeing now and the training it had in the past. It picks the responses that have a high probability of being appropriate. In the YouTube video, the presenter tried to have the same conversation the following day and got a much calmer seeming version of GPT-3. This is based on the randomness in the model. So randomly, happening multiple, probably billions of times per second, we have a network of 175 billion measures calculating probabilities and a random selection of equally valued responses in the processing. The outcome is on one day, kill all humans, and on the next, we can build a great world together. At the moment, GPT-3's ability to kill all humans is thankfully severely limited. But when all of Tesla's cars and robots are connected together via the dojo, it's going to be a much bigger decision to turn it off than simply turning off a single car or robot if something unpleasant happens. And it may be smarter than us by the time we decide to try. There's an idea called the singularity, the point at which learning machines achieve parity with us and then continue at exponential pace past us. If you're religious, you may think that there is something inherent that we can't replicate in a machine, so we're safe. But so far, there's little evidence for that. In fact, there are some scientists that say that our brains are in fact just neural networks and work in the same way as these machines. All we're really doing is selecting the best responses based on our learning and programming. The only difference between our neurons and theirs is that ours are squishy. Ray Kurzweil, computer and AI expert, predicts the singularity will happen by 2045. That's 26 years, but it could be sooner. I think that Tesla is building a platform to take the next step in AI evolution with the dojo. The dojo will dramatically speed up the evolution of Tesla's AI. One of the things that we understand about evolution is that it is a resilient, durable process. It will evolve something. It's also slippery. It doesn't really matter if it's biological or not. It often evolves unexpected solutions. It's very difficult to direct evolution towards the solutions that we may want. It's not always going to give us what we expect or even what we want. I confess I don't understand people who aren't at least somewhat nervous about this idea. It seems rather naive to me to take that stance. In an interesting interview with an AI expert talking about the singularity, he says it could be here by as early as 2030, and then our best hope is to teach them to be nice to us. That hasn't been going so well so far with humans. We've tried that for a few thousand years. I think that we need rules and laws, and we need them soon, and Elon Musk agrees. Thank you for watching.